Hey there, everybody. I'm excited because we're going to start a new unit, rocks and minerals. And we always start with minerals because minerals make up rocks. All right. So we're first going to start this presentation. And what you see is that beautiful gem or piece of jewelry called the Hope Diamond. And there's lots of history behind it. And I believe it's on display at the Smithsonian Institute in Washington, D.C. At least it has been in previous years. All right. So what are minerals? Well, first, I always like to start with a series of questions, allowing you to figure out that definition on your own. So, which of the following is not a mineral? Here are a series of well-known metals: iron, nickel, steel, and lead. One of those following is not a mineral. Right? Which one is it? And the answer is steel. But why? Why is steel not considered a mineral? And that's because steel is not natural. It is man-made. So the first rule of minerals is all minerals must be found in nature. Okay, so they can't be what's called artificial or synthetic, which means we as people can't make them. All right. All right, next one. Which of the following is not a mineral? These are four well-known gemstones. You might have them as one of your birthstones: a diamond, a pearl, a ruby, or an emerald. Which one is not considered a mineral? And the answer? The pearl. Okay. Now, some of you might have just finished reading that book before the quarantine. And so you might know how pearls form. So pearls form inside shellfish, usually oysters and clams. Okay. Now that is still considered natural, but we say minerals can't come from living things. So pearls are considered organic. So in order to be a mineral, minerals must be what's called inorganic, not organic, not from something that had organs inside their body. All right. So our teeth aren't considered to be minerals, even though they may have the characteristics of a lot of minerals found in nature, which is why we brush with fluoride. All right. And add calcium and things like that are normally found in nature. Our teeth are not considered to be a mineral. Either are the tusks of elephants, ivory. Okay, it might be valuable. Right? You should never buy it, so animals don't have to die, but they're not considered minerals. All right, next. Liquid water, so which is not the mineral? Liquid water, snowflake, salt, or gold? All right, which one? And the answer is A, liquid water. Okay, so liquid water is not considered to be a mineral. And the reason why is because water is a liquid. All minerals must be solids. So when water freezes and becomes maybe a snowflake or ice, it is then considered to be a mineral. All right. So that's another important requirement. All minerals must be solids. So if you ever bought mineral water, what they're talking about is the dissolved minerals, the magnesium and the iron that are in that water, not actually the liquid itself. All right. Next up. Which of the following is not a mineral? Ice, quartz. Quartz is mainly the sand at the beach. Fluorite, or glass. Okay. Now, a lot of you might get the answer right, but for the wrong reason. And the answer is glass. But it's not because glass is man-made. All right. There is natural glass from volcanoes called volcanic glass. Maybe you've heard of obsidian, which is a shiny, sharp-edged black rock. Okay, it's very common. And that is formed from a volcanic eruption. But the reason why glass is not considered a mineral is actually the most important definition or requirement, of a mineral. We call it the crystal structure. Glass does not have a crystal structure. So the crystal structure is this repeating arrangement of the atoms. So if you look inside a mineral, it has a very organized structure. The atoms are aligned in a pattern that repeats. And the atoms inside glass are very randomized. They don't have any sort of pattern. So we say they're non-crystalline, all right? Which means there's no way it could be a mineral. So here's the mineral definition. So if you look at all those questions and put them together, a mineral is a naturally occurring inorganic solid with a crystal structure. And then there's one other part, a definite chemical composition. That's something you actually learned last year, like the molecular formula. Like water is H2O. It's always two H's to one O. Okay, we call that its definite chemical composition, which I have here in notes. So the definite chemical composition is that a mineral will always contain certain elements in definite proportions, which means the elements are always going to have a certain ratio. So for example, a common mineral, the salt we eat, table salt, is known as halite. That's its real name. Halite is sodium chloride. Okay, so that means for every one sodium, there's one chlorine. If there was two sodiums, two NAs, Na sodium, and one chlorine, then we can't call it halite. So basically, it's the same thing as its molecular formula. So by saying there's a definite chemical composition means that molecular formula cannot just change. All right, crystal structure. I mentioned what it is. It's the repeating arrangement or pattern of atoms. It determines all other physical properties, which we're going to do in the next lesson. So for example, like how hard is the mineral? How does it break? Why is it a certain color? All these things are predetermined by the crystal structure. So I like to compare the structure of the mineral to your DNA. So our DNA determines our hair color, our eye color, probably how tall we're going to be. It determines a lot of physical characteristics that we have no control over. Same thing with a mineral. So the mineral doesn't have a DNA. Instead, it has a repeating pattern that determines how it grows, determines how it breaks, determines how it gets scratched, or how easy it is to get scratched. So I like to think of the crystal structure as the mineral's DNA. So here's salt. Salt always forms a cube. And it forms a three-dimensional cube. And it always forms in the same pattern. So this thing I'm moving around is trying to show the three-dimensional pattern or the crystal structure of salt. Okay, so you could click on that because this whole slideshow is attached to the Google Class, and you could bring that up as well. Okay, and I have another one just like that. So here's on the left is a mineral called galena. Galena always forms cubes, and the right is quartz. Quartz always forms a hexagon. So if you look at them three-dimensionally, the galena is pretty much the same exact structure as salt that we just looked at, and quartz is a little more complex. It forms a six-sided. I have another video in a minute that shows you how these atoms arrange in a structure. Okay, so we're going to watch the video now.
beneath the geysers and hot springs of Yellowstone caldera lies a magma chamber, produced by a hotspot in the Earth's mantle. As the magma moves towards the Earth's surface, it crystallizes to form young, hot, igneous rocks. The heat from these rocks drives groundwater towards the surface. As the water cools, ions precipitate out as mineral crystals, including quartz crystals from silicon and oxygen, feldspar from potassium, aluminum, silicon, and oxygen, galena from lead and sulfur. Many of these crystals have signature shapes. Take this cascade of pointed quartz, or this pile of galena cubes. But what causes them to grow into these shapes again and again? Part of the answer lies in their atoms. Every crystal's atoms are arranged in a highly organized, repeating pattern. This pattern is the defining feature of a crystal and isn't restricted to minerals. Sand, ice, sugar, chocolate, ceramics, metals, DNA, and even some liquids have crystalline structures.
So yeah, it's not just minerals, but in order to be a mineral, this is a requirement. So sugar definitely has crystals in it. Okay, it's an organic crystal. All right. However, since sugar comes from something organic, it doesn't fit the rest of the requirements of a mineral that I went over. Either does chocolate. Okay.
Each crystalline material's atomic arrangement falls into one of 6 different families: cubic, tetractyl.
So these are the main shapes a crystal can grow into:
triclinic, and hexagonal. Given the appropriate conditions, crystals will grow into geometric shapes that reflect the arrangement of their atoms. Take galena, which has a cubic structure composed of lead and sulfur atoms. The relatively large lead atoms are arranged in a 3-dimensional grid 90 degrees from one another, while the relatively small sulfur atoms fit neatly between them. As the crystal grows, locations like these attract sulfur atoms, while lead will tend to bond to these places. Eventually, they will complete the grid of bonded atoms. This means the 90-degree grid pattern of galena's crystalline structure is reflected in the visible shape of the crystal. Quartz, meanwhile, has a hexagonal crystalline structure. This means that on one plane, its atoms are arranged in hexagons. In 3 dimensions, these hexagons are composed of many interlocking pyramids made up of 1 silicon atom and 4 oxygen atoms. So the signature shape of a quartz crystal is a 6-sided column with pointed tips. Depending on environmental conditions, most crystals have the potential to form multiple geometric shapes. For example, diamonds, which form deep in the Earth's mantle, have a cubic crystalline structure and can grow into either cubes or octahedrons. Which shape a particular diamond grows into depends on the conditions where it grows, including pressure, temperature, and chemical environment. While we can't directly observe growth conditions in the mantle, laboratory experiments have shown some evidence that diamonds tend to grow into cubes at lower temperatures and octahedrons at higher temperatures. Trace amounts of water, silicon, germanium, or magnesium might also influence a diamond's shape. And diamonds never naturally grow into the shapes found in jewelry. Those diamonds have been cut to showcase sparkle and clarity. Environmental conditions can also influence whether crystals form at all. Glass is made of melted quartz sand, but it isn't crystalline. That's because glass cools relatively quickly, and the atoms do not have time to arrange themselves into the ordered structure of a quartz crystal. Instead, the random arrangement of the atoms in the melted glass is locked in upon cooling.
Okay, so they just went over why glass isn't a crystal. So if you never understood how they made glass, they melt down quartz. So they actually melt down something that is a mineral. They're basically turning the quartz back into lava. And then they force it to cool very fast. And then they could shape it as it cools. But when it cools quickly, that hexagon structure that quartz has that we saw in the video doesn't have time to form. So instead you have this randomized locking of elements without a true structure behind it. And the same thing happens with volcanic glass. So with volcanic glass, it's evidence of a rapid eruption, which means magma from deep within the earth got shot out very quickly as a lava ball into the cold atmosphere. And it hit the cold atmosphere and basically froze instantly. So that's a good way of thinking of volcanic glass. It's just like lava that froze immediately, and it didn't have time for the crystals to grow or take shape. Oh, all right, I moved on, which is fine. We got the basis of the video right there. So how do minerals form? They form two major ways. One, from cooling magma or lava. So if the magma cools slowly, the crystals will have time to grow. So for example, with glass, it cools so fast, it doesn't even have any crystals. So the longer it takes for magma to cool, that's where you could get like really tremendous crystals that people would want to put in a museum or have on display in their home possibly. So if magma cools slowly, crystals will have time to grow and get large. If magma cools quickly, well, then it's really lava because it's probably outside the volcano. Crystals don't have time to grow, so they will be small. Okay, so the rule of thumb when we look at a rock is if the rock formed from magma, the crystals are large. Instead of saying large crystals, we say coarse-grained. And if the crystals are small, rocks that form from lava have very small crystals. So if you pick up a type of rock known as igneous, if you can actually see the crystals with your eye, then you're actually holding a rock that formed from magma deep under the ground. If you pick up an igneous rock and you can't see the crystals, then you've picked up a rock that formed from an eruption, which means it came from lava. All right, minerals from seawater. So seawater is a mixture. It's got water and dissolved elements in it. So since it's a solution, if the solution is supersaturated, which means like kind of overfilled with a material, then the minerals will precipitate out. Just like with my coffee. If I start to put way too much sugar in the coffee, the sugar will start to fall to the bottom. All right? So if you ever had iced coffee, you're well aware of that. You put too much sugar in, then you're sipping up solid sugar. All right? So water can allow crystal formation. Precipitate means to fall. All right? So we use the same term for rain. So rain will precipitate out of the clouds. If seawater begins to evaporate, it will leave dissolved minerals behind. So basically, there's two ways minerals can form from seawater. It's just supersaturated, like the Dead Sea in Israel, that the salt is just combining and falling, and you get like a mud of salt on the bottom of that sea. Or the water in the sea is evaporating, leaving behind all the dissolved salt or whatever minerals were dissolved in the seawater. Usually it's three major minerals: calcite, which makes up seashells; salt, which we know about; and another mineral called gypsum. Sometimes another mineral that's similar to calcite called dolomite is also in seawater. So it's the same rule of thumb. So as the magma, if seawater evaporates slowly, then the crystals will have time to grow. So you'll get a very large crystal. And if the seawater evaporates quickly, then the crystals won't have time to grow. So they'll be small. So here's just a time-lapse video. Some of you might recognize this song. It's from one of the Marios. You could buy this crystal growing kit on Amazon, I believe. So this probably took a day. if they cooled the solution really fast, you wouldn't get such a nice shape forming. So the fact that they let it cool slowly, it had time to grow. Pretty cool. And then you could put a light under it. All right. So that's the lesson. All right. If you have questions, email me or wait to the Google Meet and please ask them. All right. And, if you have minerals, some of you might have collected them as a young kid. I know I did. I know my kids do. And you want to know what they are, send a picture of them. Maybe I can identify them. Usually this unit is a lot more fun because it's so hands-on. And, we actually look at the minerals and do physical tests. But that's difficult to do with this distance learning that we're going through. All right. Have a great day.